On July 1, 2025, a small telescope in the mountains of Chile picked up something barely visible moving across the sky. At first, it looked like nothing more than a faint dot of light. But that tiny dot was about to become one of the most remarkable objects astronomers had ever studied. It was 3I/Atlas, only the third confirmed interstellar object ever seen passing through our solar system. And what scientists discovered over the following year was far stranger than the first blurry image suggested. Not because of aliens. Not because of mysterious signals. The real story is already astonishing enough. Because this comet may be older than our Sun. Think about what that means. Our Sun is about 4.6 billion years old. Earth, Mars, Jupiter, and every other planet in our solar system formed around it from a vast cloud of gas and dust. But 3I/Atlas may have existed before any of that happened. It could have formed around another star billions of years ago, possibly around a star that died long before our own Sun was even born. While our solar system was still nothing more than a cloud waiting to collapse, this frozen piece of rock and ice may already have been drifting through the galaxy. For billions of years, it traveled through the darkness without ever coming close enough for anyone to see it. Then, completely by chance, its path crossed ours. But how did astronomers know it came from somewhere else? The first clue was its orbit. The object was discovered by ATLAS, the Asteroid Terrestrial Impact Last Alert System, a network designed to scan the sky for objects that could potentially threaten Earth. When ATLAS spotted 3I/Atlas, the comet was still roughly 410 million miles from the Sun, around the region of Jupiter's orbit. In that first image, it was just a moving speck. But its motion immediately raised a much bigger question. Its path was hyperbolic. In simple terms, it was not trapped by the Sun's gravity. It was passing through. Planets and most comets in our solar system travel on closed orbits. They come around the Sun and, unless something changes their path, they keep coming back. 3I/Atlas was different. It was moving through our solar system on a one-way journey. It would pass the Sun once, gain or lose speed because of the Sun's gravity, and then continue back into interstellar space. That is the signature of an object that did not originate here. Suddenly, this faint dot became only the third confirmed visitor ever seen from another star system. The first was 1I/Oumuamua, discovered in 2017. It was strange, faint, and moving so quickly that astronomers had only a short time to study it. The second was 2I/Borisov, discovered in 2019, which looked much more like a conventional comet but was still too distant and faint for the kind of detailed investigation scientists wanted. Two visitors had come and gone, leaving behind more questions than answers. Then 3I/Atlas arrived, and this time the situation was completely different. This comet was larger and brighter, giving astronomers something they had never really had before: time. Estimates placed its solid icy nucleus somewhere between roughly 440 meters and 5.5 kilometers across. That uncertainty itself shows how difficult it was to measure such a distant object, but even the lower estimates made it substantial. And unlike the first two interstellar visitors, 3I/Atlas could be followed for months using powerful instruments on Earth and in space. The race to study it began almost immediately. Because the comet was moving incredibly fast, every observation mattered. When it was first detected, it was traveling at around 137,000 miles per hour. As it fell deeper into the Sun's gravitational field, its speed increased, reaching roughly 153,000 miles per hour around its closest approach in late October 2025. That is around 200 times faster than a commercial passenger aircraft. So what happens when you try to study something moving that fast? You bring out the biggest tools available. One of the most important was the James Webb Space Telescope. Webb was designed to study some of the most distant galaxies and stars in the universe. It was not built specifically to chase a comet racing through our own solar system. Yet astronomers managed to point it toward 3I/Atlas and, by August 2025, obtained a detailed spectrum of its light. A spectrum is essentially a chemical fingerprint. When scientists break an object's light into its component wavelengths, they can see clues about the gases and materials surrounding it. And Webb's results revealed something particularly interesting: an unusual abundance of heavy water. Ordinary water contains 2 hydrogen atoms and 1 oxygen atom. Heavy water is similar, except that one of those hydrogen atoms is replaced by deuterium, a heavier form of hydrogen. The ratio between ordinary water and heavy water can preserve clues about the environment where an icy body formed. It is like a chemical record of the conditions that existed billions of years ago. And the ratio observed in 3I/Atlas appeared unusual compared with comets from our own solar system. That raised a fascinating possibility. This comet may have formed in a much colder environment around a much older star. But could another instrument confirm what Webb was seeing? Astronomers turned to ALMA, the Atacama Large Millimeter/Submillimeter Array, high in the Chilean desert. Its collection of radio antennas is capable of detecting incredibly faint chemical signatures. ALMA observations provided additional evidence that the water associated with 3I/Atlas was unusual. The measurements suggested that the comet formed under conditions different from those that shaped the familiar comets orbiting our Sun. That mattered because scientists were no longer simply looking at a rock from another place. They were beginning to reconstruct the environment of an entire star system that existed long before our own. Then came more observations from the European Southern Observatory's Very Large Telescope in Chile. By early 2026, astronomers had gathered detailed images and spectra as the comet continued its journey. The chemical clues pointed toward a cold, distant formation environment consistent with the outer regions of an older planetary system. That possibility makes 3I/Atlas extraordinary. Imagine holding a piece of ice from a neighborhood that may have existed before our own neighborhood was even born. The object could be carrying a physical record from a completely different chapter of the galaxy's history. And the deeper scientists looked, the more interesting that record became. In December 2025, NASA's SPHERE-X mission also observed the comet in infrared light. SPHERE-X is designed to survey the entire sky, but its observations of 3I/Atlas provided another look at the cloud of gas and dust surrounding the nucleus. As sunlight warmed the comet, material began escaping from its surface. Scientists detected signatures associated with water, carbon dioxide, dust, and organic molecules. In one sense, this was familiar. Comets in our solar system do the same thing. Their ice warms, gases escape, dust is released, and a glowing coma develops around the nucleus. But that familiar behavior made the strange chemistry even more valuable. The object behaved like a comet, yet its ingredients appeared to have come from a very different place. And then another molecule gave scientists an even deeper clue. In the spring of 2026, researchers studying new Webb observations reported a direct detection of methane coming from 3I/Atlas. Methane may sound ordinary, but in this context it was important. Its presence could tell scientists more about the temperature and chemistry of the disk of gas and dust where the comet originally formed. That disk belonged to a star system we may never be able to identify. The star itself may have disappeared billions of years ago, but something it produced was still traveling through space. Piece by piece, the comet was revealing information about a cosmic neighborhood that no telescope could ever visit directly. Yet the biggest surprise was not happening millions of miles away. It was happening much closer to Mars. During its journey through the inner solar system, 3I/Atlas passed relatively near Mars in October 2025. Several spacecraft already operating around the red planet had an unexpected opportunity to observe it. These missions were not designed to study interstellar comets, but their cameras could be turned toward the passing object. European spacecraft captured observations, and NASA missions also contributed to the effort. Then, in 2026, China's Tianwen-1 mission was able to obtain particularly valuable images as the comet passed through the region. This was an incredible technical challenge. The comet was small, faint, and moving at roughly 58 kilometers per second. Its apparent motion relative to the observing spacecraft could be even more dramatic. The camera involved was built primarily to study Mars, not to chase a tiny object flying through darkness at extreme speed. Yet astronomers managed to track it. The resulting observations gave scientists some of the closest views ever obtained of an interstellar visitor. For a brief moment, instruments that had been built for completely different missions became part of a worldwide effort to study something that would never come this way again. And the observations did not stop there. In January 2026, NASA's Transiting Exoplanet Survey satellite, better known as TESS, was temporarily redirected from its normal planet hunting work. For about a week, it monitored the region through which 3I/Atlas was traveling. TESS normally looks for tiny changes in the brightness of distant stars that can reveal planets passing in front of them. But that same ability to make precise, repeated measurements could be useful for tracking a comet. By watching the object's brightness over time, scientists could look for changes as it moved away from the Sun and its surface cooled. A spacecraft built to find worlds around other stars had suddenly been recruited to study a worldless visitor from another star. All of this happened under an unforgiving deadline. 3I/Atlas was never going to stay. It approached the Sun in late October 2025, passing safely outside Earth's orbit. There was never a threat to our planet. The Sun's gravity accelerated the comet as it came in, then sent it back outward on its original interstellar trajectory. After its close pass, the comet began climbing back into the darkness. By around March 2026, it had moved back beyond Jupiter's orbit. And every day after that, it became harder to observe. The door was slowly closing. But what exactly would happen when it finally disappeared? Nothing dramatic. There would be no explosion, no final signal, and no sudden ending. It would simply become too faint for our instruments to detect. Then it would continue traveling through interstellar space. It would leave the solar system just as it entered it, on a path that will carry it away forever. The Sun briefly changed its speed and direction, but it could not capture the comet. There will be no second visit. No mission can wait for it to come back. No telescope can schedule another observation decades from now. The measurements collected during this brief encounter are essentially our entire opportunity to study it. That is why the response from the scientific community was so intense. Telescopes in Chile watched it from the ground. The James Webb Space Telescope turned its attention toward it from space. ALMA examined its chemistry. SphereX studied its glowing cloud. Mars spacecraft pointed their cameras toward the sky. TESS temporarily changed its mission to monitor the comet. Scientists across NASA, the European Space Agency, the European Southern Observatory, China, and other institutions all contributed observations. Different spacecraft, different instruments, different missions, all focused on the same tiny visitor. And they were racing against something no scientist could control: time. What did all that effort reveal? The most important discovery may be the simplest one. 3I/Atlas is genuinely from outside our solar system. Its trajectory provides strong evidence that it was not born here. Its chemistry gives scientists clues about a formation environment unlike our own. Its unusual water measurements, gases, dust, and organic material offer a rare glimpse into the ingredients of another planetary system. And perhaps most astonishing of all, the evidence suggests that this object could be extraordinarily old, potentially older than the Sun itself.